In our first set of practice problems here, we're just making sure we understand what acids and bases are and what we can know about strong versus weak. So in our first set of examples, you can see what I've labeled as the acids and the bases and the conjugates. When you are trying to determine what an acid or base is, sometimes the formula by itself is enough information. For example, these two things, which are labeled as bases, have to be a base in this circumstance because they don't have any hydrogen to give. Therefore, by default, the first things would be acids. When we're labeling the right side, we can establish or think about this in two ways. We can think, well, the acid turns into the conjugate base, so the base would be the thing that has one fewer hydrogen ions than my acid. Or I could look at this in terms of the reverse reaction, which gives it away and which accepts the hydrogen. Both of those definitions will get us to the exact same answer. So it's all about, with the information that you're given, answering it in the most simple way possible for you. Down here, for example, the HClO3, HSO4 minus, maybe we know by our naming conventions or other definitions what the acid or base is. But here, since they both start with hydrogen, it is really important to be looking at the process of change to understand what's defined as the acid or base. Another thing that you could be asked, instead of just what's everything that's an acid or what's everything that's a base, is be asked about a conjugate acid-base pair. A conjugate pair is one that differs by a hydrogen ion. So they're going to have one difference in terms of the number of hydrogens and one difference in terms of the charge. The acid always has more of each of those. It has one more hydrogen and a charge that is one higher. So my acid to my base and my acid to my base, and they are conjugates of one another. Although these are the HClO and the NH3 and acid base that are on the same side of the reaction, they are not conjugates of one another. Looking down here, we've got different formulas going on. We've got different numbers of hydrogens, all different places. The key, though, is the losing or the gaining of one hydrogen ion as we turn from an acid to a base. You'll see most acids that we deal with do start with hydrogen, although there are some, actually very many, that are organic acids that will have the formula COOH at the end. And you'll see a lot of our bases are either negative ions or have nitrogen as a part of their formula. Down here on part C, it's a very vague prompt. So by itself, this would not be a good question for a quiz for the AP test, either in multiple choice or free response. It would ask something much more specific. But this helps us to not only practice our definitions of acids and bases and conjugates, but to clarify what it means to be strong or weak. So here it's asking, or I am answering, I guess, well, what's stronger? So here I have an acid and a base, and an acid and a base. Out of the two acids, because the forward reaction is very favorable, but the reverse barely happens at all, that's my indication that HNO3 is a stronger acid than hydronium, and H2O is a stronger base than NO3 minus. NO3 minus and H3O in this circumstance or this set of chemicals is barely able to do that reverse reaction at all. H2SO3 is sulfurous acid reacting with water. So a very similar look right here, but it is written as an equilibrium because H2SO3 is not one of our strong acids. In this case, we know that the reverse reaction has to be more favorable. Later, we will be given specific equilibrium values or K values that tell us about the left side versus the right side in terms of favorability. But as a general definition, all weak acids dissociate very little. So that means that that forward reaction is going to be far less favorable than the reverse reaction. So knowing that, this is better at accepting a hydrogen, and this is better at giving a hydrogen than these two are. And this third one's very weird. I don't know where or why I came up with this, but did just want to show that it's not always about memorizing a list in terms of a definition. HI is one of our 6 strong acids. HBr is one of our 6 strong acids. In this reaction, they are not both acting as acids. They are acting as an acid and a base. The HI gives away its hydrogen, the HBr takes that in. Although this would take a very weird circumstance to make this happen, probably not even an aqueous solution. But the point is, it's not based upon definitions that we've memorized. It's based upon applying it to the circumstance that we are in. HI is a stronger acid than HBr. So if we had a circumstance of just reacting the two of them, HI would give its hydrogen away and HBr would accept it, making a conjugate acid and a conjugate base here. Don't really know which side would be favorable without knowing a lot more about that equilibrium. So here, just making sure we know the definitions, we know conjugates, and we can conceptually apply the idea of strength.